Late in the year 1967, we witnessed the beginning of the second decade of the space age. It is difficult to realize that only 10 years ago, at the end of December 1957, the United States had scarcely begun the exploration of space. We had yet to launch our first satellite into Earth orbit. For now, in early 1968, we have acquired a vast amount of new information from a multitude of unmanned satellites and from 2 completed programs of manned space missions. We have our sights trained on manned exploration of the moon and on manned scientific investigation in space laboratories. There is still much to be done before we accomplish even our immediate objectives in space. But events in the last 3 months of 1967 have greatly increased confidence that our technology is sound and strengthened belief that we will succeed. During the last 3 months of 1967, the spotlight turned to the major phases of work that must still be accomplished before Apollo will be ready for manned flights, first in Earth orbit, then to the moon. In the development of the spacecraft, the lunar module was the focal point of attention. The lunar module, built by Grumman Aircraft, is of course the part of the spacecraft that will land astronauts on the moon's surface. An important series of lunar module tests was about to get underway in a large chamber at the Manned Spacecraft Center in Houston, Texas. In the chamber, the lunar module, manned by astronauts, will be subjected to a simulated space environment, that is, a near vacuum and extreme temperatures. These are among the many conditions under which the lunar module and its systems are being proven before it will be sent into space on a manned flight. Another important series of lunar module tests was being readied at the Manned Spacecraft Center to assure that the cabin is safe in the event of fire. To help assure safety, there have been over the past months many design and material improvements, many individual investigations. To test innovations in the cabin, fires have been deliberately started at a variety of potential sources, in a variety of conditions, and the flame behavior studied. In the forthcoming series of tests, it must be proven that cabin fires will tend to localize and die out rather than spread dangerously. This will remove a critical restraint on manned Apollo flights. One of the most trying series of lunar module tests was in progress at NASA's White Sands Test Facility in New Mexico. Here, for months, engineers and technicians have been confronted with technical problems in getting the lunar module ascent engine to burn with consistent stability. The ascent engine must launch the module and flight crew from the lunar surface into orbit about the moon. Rocket engine stability problems are among the most difficult in the aerospace industry. For the lunar module ascent engine, a variety of modifications have been tried, and test results late in 1967 indicated that a solution was at hand. It was anticipated that final qualification testing would begin early in 1968. Meanwhile, the manufacturing of lunar modules continued at Grumman Aircraft. The second lunar module equipped for flight was in final factory checkout and was scheduled to be ready for delivery in early 1968. The first lunar module planned for a manned flight was also in factory checkout, scheduled for shipment to the Kennedy Space Center, Florida, in the spring of 1968. As with the lunar module, there is still much to be done to get the command and service modules ready for manned flights. Built by North American Rockwell, the command module contains working and living quarters for a 3-man flight crew. The service module contains a propulsion system and other flight equipment. Here, too, hardware was being prepared for tests with men while in a simulated space environment, where it must be proven reliable before it is committed to manned missions. And as with the lunar module, an important series of tests was being readied to assure that the command module cabin is safe in the event of fire. The series will culminate a period of intensive work to increase the safety of designs and materials. The command and lunar module cabins have been considerably improved. Moreover, much has been learned that will be of benefit in the development of future manned spacecraft as well as commercial applications. There were also in progress tests to prove the command module's Earth landing system. The landing system has been modified slightly because the weight of its burden, the command module, had been somewhat increased by design and material changes inside the cabin. This meant that the tests had to be extended beyond original plans to assure complete confidence in the landing system. While the test activities we have covered, as well as many others, were in progress, North American Rockwell continued its manufacturing work. The company was conducting final checkout for the command and service modules scheduled for the first manned Apollo flight, which will be launched by an uprated Saturn I. The company was also conducting final checkout for the modules scheduled for the first manned flight aboard the far larger Saturn V. While everything possible is done during ground testing and manufacturing to assure reliability, the success of these efforts cannot be truly measured except by flight. And at the end of 1967, major attention focused on the Kennedy Space Center's Complex 37, for it is from here that an operational lunar module will be fired into space for the first time unmanned on an uprated Saturn I. The only major piece of Apollo equipment which has yet to fly with operating systems, the lunar module will be put through a rigorous test in Earth orbit. Its structures, both its engines, its onboard systems will be tested. In the most critical phase of the mission, the lunar module will be put through an abort maneuver which would be required should an emergency develop just before touchdown on the lunar surface. Months were spent getting the lunar module ready for flight. Finally, in November 1967, it was installed inside its adapter assembly and transported to the pad for final launch preparations. In the huge vehicle assembly building at Complex 39, meanwhile, the second Apollo Saturn V was being prepared for an unmanned launch. According to plans, the second flight will be almost a repeat of the first, the primary objective being to solidify confidence in the vehicle, which will eventually carry American astronauts to the moon. The astronauts, in the meantime, were themselves hard at work. One of the many skills they must perfect is that of joining two Apollo vehicles in space. As we proceed in Apollo to manned lunar flights, there is no scientific objective more important than the study of the moon. For therein are long-sought answers to many questions about the solar system and our own Earth. Study of the moon from space has thus far been carried out in unmanned missions, such as the flight of the 6th Surveyor spacecraft, which successfully set down in the very center of the face of the moon in early November 1967. The unmanned investigations so far have been primarily directed at mapping the moon and studying its surface. For example, the bearing strength, the chemical content, the soil consistency. In Apollo, when man visits the moon firsthand, many of the studies will revolve around data received from an array of instruments known as a Lunar Surface Experiment Package. These instruments, well along in their development at Bendix at the end of 1967, will gather and transmit information to Earth long after departure of the flight crew. Science will learn, for example, much about the geologic structure of the moon, about the nature of the moon's very core, about storms of radioactive particles which originate with our violent sun. Science will also learn much from samples which astronauts bring back from the lunar surface. It is at a recently completed Manned Spacecraft Center laboratory that the samples will be isolated from Earth contamination and prepared and distributed to scientists in this country and abroad. The history of the moon's formation can be studied, the magnetic characteristics, the chemical constituents, possible signs of life. At the end of 1967, most of the laboratory equipment had been installed and was being checked out, and the techniques for handling the samples were being developed and perfected. Scientific investigations in space, the advancement of technology, extended studies of man's physiology will assume even greater prominence in Apollo applications, the program to capitalize on our aerospace capabilities. Late in 1967, Apollo applications equipment was taking shape in facilities across the country. Part of the equipment is an uprated Saturn I second stage, which has been modified so astronauts may convert it in space from a rocket to living and working quarters. By the end of 1967, McDonnell Douglas had completed modification of a full-scale model of the special stage, called the Orbital Workshop, to reflect latest design concepts. For instance, the company installed 2 new floors, in effect dividing the workshop into 2 sections so that better advantage could be taken of working space. At the Marshall Space Flight Center, Huntsville, Alabama, engineers worked with a partial model of the workshop underwater, where the weightless conditions of space may be fairly well simulated, to evaluate designs and to study equipment installation procedures. Concurrently at Marshall, a full-scale model of a telescope mount was modified to reflect latest design concepts. Connected with the orbital workshop, this equipment will serve as a place to mount a battery of telescopes for astronomical observations. Engineers worked with a partial model of the mount underwater to help evaluate designs of equipment requiring work outside the telescope mount. Beyond models, hardware was in the early stage of fabrication. For example, assembly was in progress for solar panels and solar cells. A part of the telescope mount, the solar panels, will draw on the energy of the rays of the sun for electric power. The accomplishment of what our nation wants to do in Apollo and Apollo applications is an imposing and difficult task. Few events have been more imposing and difficult, and few have been more rewarding than the flight of Apollo 4. While While the flight of Apollo 4 was, in its own right, a major milestone for 1967 and a technological achievement of the first magnitude, its primary significance for the program was that it proved we are on the right course, that the efforts of hundreds of thousands of people have been well spent, that we may now proceed with greater confidence in the future. The unmanned Earth orbital flight was the first for the Saturn V launch vehicle for the lunar mission, and the third for the Apollo spacecraft. The success of the mission proved much indeed. In brief, it proved that pre-flight checkout procedures at factories and test facilities across the nation, as well as at the launch site, are valid. It proved the capability of the launch team, which spent many months assuring that Apollo 4 was flight-worthy. It proved that launch complex ground facilities were well designed. It proved that Apollo Saturn V could be launched at a predetermined time, as required for lunar missions. In fact, liftoff came within 1 second of the planned moment. Soon became obvious that something else was being proven. Apollo Saturn V, by far the largest, most complex space vehicle ever built by this nation, would fly superbly. As the mission progressed, the capability of the flight control team was proven. The capability was proven for mission support facilities, the Mission Control Center, a world-encircling network of tracking stations, tracking ships, tracking aircraft. It was proven that the launch vehicle's hydrogen-fueled third stage would reignite in space, as required for the lunar mission. After the spacecraft climbed to the peak altitude of the flight, more than 11,000 miles, and began its descent to Earth, one final thing was going to be proven, that the command module could withstand the heating of re-entering the atmosphere at a velocity even greater than that anticipated for lunar missions. The standards set by Apollo 4 will be hard to match in the months to come. If we can live up to the standards, however, we may proceed into the second decade of the space age, confident that our achievements will surpass those of the first decade. We may feel confident that we can successfully accomplish what must yet be done to meet our present goals in space, and confident that we will be able to meet our future goals as well.